You are standing on a low hill, and it is the wrong shape for a hill. It runs dead straight. It goes away to your left until the heat haze eats it, and away to your right until the heat haze eats it. The same height and the same width the whole way, with a footpath worn along the top. You are in Cambodia. It is the middle of the 12th century, the end of the dry season, and the air is doing that thing where it presses on your chest. Down on one side there is a plain of stubble and sugar palms and low wooden houses standing on little earth mounds. And on the other side, held up above the level of that plain by the bank under your boots, there is water. An enormous amount of water. It runs out to the horizon. There is no far shore you can see, just a smudge, and out in the middle of it a small stone temple sitting on an island, and you would swear on anything you like that you are looking at a lake. You are not. There is no lake here. Every drop of it is being held up by a wall that men built with baskets and their hands and their backs, and that wall is under your feet, and it is about 5 miles long. Now turn round. Look southeast over the palms. A couple of miles that way above the tree line, there are 5 stone towers shaped like lotus buds. If you have ever seen a photograph of this country, you have seen those towers. Everybody photographs those towers. Almost nobody photographs the thing you are standing on. And that is the sentence this whole story turns on. The towers are the small part. The temple, the carvings, the causeway, the moat that people line up beside at sunrise to get the reflection, all of it is the ornament on top of the machine. The machine is the ground itself. It is banks and channels and vast shallow reservoirs laid out across a piece of country the size of a modern city. And its job is to catch one entire wet season and then spend it carefully through 6 dry months in which almost nothing falls. It has no pumps, not one, anywhere in it. It runs on gravity alone, across a plain so flat it drops about a meter in every kilometer. And in a few hundred years, that machine is going to be the leading suspect in why all of this stops. My name is Dan. I am a structural engineer, and I want to open with the least glamorous sentence in my entire trade. Almost none of the buildings I have watched go wrong went wrong because somebody got the structure wrong. The columns were fine. The beams were fine. The steel is nearly always fine. What kills buildings is water. Water in the wrong place. Water sitting in a joint nobody detailed properly. Water coming off a roof faster than the drainage was ever sized to carry, because the drainage was sized decades ago for rain that does not fall like that anymore. I have spent more of my working life on falls and gullies and gradients than on anything you would call heroic. So when people talk to me about Angkor and want to talk about god kings and carved goddesses and the stone faces on the towers, I nod along politely, and the entire time I am thinking about the drains. Because Angkor is not a temple with a city around it. Angkor is a water engineering project roughly the footprint of a modern metropolis, with temples sitting on it. It is, I think, by a comfortable distance, the most ambitious civil engineering anybody attempted anywhere before the Industrial Revolution. I want to walk you through how it actually worked, and then I want to tell you the uncomfortable part, which is that the same design that made it the biggest is our best engineering explanation for why it stopped. Start with the problem because the problem is not the one people assume. This part of Cambodia is not short of water. It gets soaked. The southwest monsoon comes in around May, and by the time it lets go in October, it has delivered the overwhelming bulk of the year's rain. And the Tonle Sap, the Great Lake to the south, does something almost unbelievable. The Mekong swells so hard that it backs up the river feeding the lake and reverses it, and the lake inflates to several times its dry season size. Then the rain shuts off, and for 6 months roughly nothing comes out of the sky at all. So the resource is not scarce. The resource is badly timed. You get a year's worth of water in 4 months and then live off it. Which means the engineering question here has never been how do we find water. It is, how do we hold what falls, keep it from wrecking us on the way through, and release it slowly enough to grow rice in February? That is a storage and distribution problem, the same one a water utility solves today with dams, valves, telemetry, and electric pumps. The Khmer solved it with earth. Just earth, moved by hand, in quantities I find genuinely difficult to picture. And the second half of the problem is the ground. This plain, between the Kulin Hills in the northeast and the Great Lake in the southwest, is almost perfectly flat. The average slope across it is about 0.1%. Let me put that in terms that mean something on site. The ground falls roughly 1 meter for every kilometer you travel. If I hand a groundworker a drainage run at 1 in 1,000, he will pull a face at me. Because at that gradient, the water barely knows which way is downhill, and anything that settles silts. Now build a city-sized water network on that. Every bank, every channel, every reservoir lip has to be set within centimeters of a level that you have to establish over kilometers of flat, hot, half-flooded ground. That is the job. So what did they build? Not a reservoir. A network, and it grew for something like 600 years, from around the 9th century onward, king by king, each one adding to what he inherited. Survey work led by Roland Fletcher and Christophe Partier, and their colleagues has broken it into parts you can actually reason about. And once you see the parts, it stops looking like decoration and starts looking like plant. First, running east to west, long embankments set across the natural fall of the land, catching water coming down off the hills to the north and northeast before it can sheet away to the lake. Those are your interceptors. Second, channels running north to south, taking the water those banks caught and delivering it into storage. Those are your mains. Third, the storage itself. The Barays, the enormous rectangular reservoirs, plus the temple moats, which are not moats in the castle sense at all but tanks that happen to be beautiful. Fourth, works running northwest to southeast, distributing water sideways across the slope into fields that would otherwise never see it. That is your distribution. And fifth, and this is the one that tells you these people had been badly frightened at least once, channels aimed southwest, whose only job is to get surplus water out of the system fast and dump it in the tunnel sap. Overflows, bypasses, a spillway strategy. Somebody at Angkor understood that the dangerous day is not the dry one, it is the wet one, and built a way to throw water away in a hurry. I have sat in meetings where getting a client to pay for that exact provision took 3 attempts. Now the Barays, because the numbers are the thing. The West Baray, the one you were standing on at the start, is about 7.8 kilometers long and 2.1 wide. Call it 5 miles by 1.1 miles. Its maximum capacity today is somewhere around 53 million cubic meters of water, which is roughly 14 billion gallons, and it is retained by earth dikes standing up to about 11.9 meters. Near enough 40 feet of hand-built embankment, holding back an inland sea. It is the only baray at Angkor that still holds water, 900 years on. Its older sibling, the East Baray, built around the year 900 under Yasovarman I, is about 7.2 by 1.7 kilometers and held over 36 million cubic meters. It is dry now. There is a temple stranded on what used to be an island in the middle of it, sitting in a field. And here is the detail that reframes the whole thing for an engineer. Those reservoirs are not holes. You do not, mostly, dig down into the plain and fill the hole. You build up. You raise banks and impound the water above the surrounding ground level. That is a completely different structure. A hole in the ground is forgiving. The worst it can do is be empty. A raised reservoir is a dam, and everything downhill of it lives inside the consequences. So the West Baray is 53 million cubic meters of water sitting up in the air above an inhabited floodplain, held there by compacted earth, with no concrete core, no steel, no clay cutoff that we know of, no geotextile, no instrumentation, no piezometers, no body monitoring seepage, and no compaction specification because the concept did not exist. Try getting that past a modern safety inspector. And yet the thing has stood for the better part of a millennium and still holds water today, which tells you the men who built it understood, empirically and very well, how to build an earth bank. Wide, low-angled, generous, with a cross-section so fat that seepage has a long, lazy path and never gets anywhere interesting. That is genuinely how you do it. It is how we do it now, with more instruments and worse manners. And there are no pumps. I want to keep saying that because it is easy to hear and hard to actually hold on to. Nothing in this system lifts water, not one component. Every single drop that moves in the greater Angkor region moves because somebody put it somewhere higher than where they wanted it to end up. That is why the Barays are raised. An impounded body of water sitting above the plain can feed the plain, and a hole in the ground cannot feed anything without a machine. So the whole layout is an elevation puzzle. Storage has to be higher than distribution. Distribution has to be higher than the fields. The overflow has to sit at exactly the right level, high enough that you do not bleed away the water you spent the wet season collecting, low enough that, when the big one comes, the surplus leaves over the top instead of through the bank, because water going through a bank is how you lose a bank. Every one of those levels is set in centimeters over kilometers, on a plane that falls a meter a kilometer. And they held it century after century with no laser level and no theodolite. Water finds its own level, so you can make an instrument out of a trough and carry it forward with pegs and string and repetition. It works. It is desperately slow. And on that plane, the error you cannot see is the one that ruins you. A channel laid a hand's breadth out of true either does not flow at all, or flows fast enough to scour its own bed and start moving sand. Which, hold that thought, is exactly what eventually happened. Now, how do we actually know all this and not just guess it? This is the part where I want to name names, because the answer is one of the great pieces of archaeological engineering of my lifetime, and it is very recent. For a long time, what you could map at Angkor was what you could see, and what you could see was mostly the stone, the temples, because they are enormous and made of rock and refuse to disappear. The rest of the city was built of timber and thatch on low earth mounds, and timber and thatch in a tropical climate return to the soil within a couple of generations. So the picture inherited by most of the 20th century was magnificent temples standing in jungle. In 2007, Damien Evans, Roland Fletcher, Christophe Partier and colleagues published a comprehensive archaeological map in the Proceedings of the National Academy of Sciences that established Angkor as the largest known low-density settlement complex of the pre-industrial world, on the order of 1,000 square kilometers. Then came the lasers. In 2012, an airborne laser scanning survey, LiDAR, was flown over about 370 square kilometers of the Angkor region, funded through the Khmer Archaeology (LIDAR) Consortium with the support of the Cambodian government and UNESCO, and published in the Proceedings of the National Academy of Sciences in 2013. LIDAR fires a great many laser pulses down from an aircraft and times the return, and its trick is that in forest, a proportion of those pulses slip between the leaves and hit the actual ground. Throw away every return that bounced off vegetation, keep only the ones that reached soil, and the canopy comes off. What was underneath was not jungle with temples in it. It was a city, streets on a grid, house mounds in their thousands, ponds, each one dug beside a household, field boundaries, embankments and channels running for kilometers out into what everyone had assumed was empty forest, tying the monuments into one continuous engineered landscape. A second, much larger survey was flown in 2015, covering something like 1,900 square kilometers, and published in the Journal of Archaeological Science the following year. And in 2021, Sarah Klassen and colleagues in Science Advances combined that laser data with excavation and radiocarbon dates and statistical modeling and put a number on it. The Greater Angkor region, about 3,000 square kilometers of it, held somewhere between 700,000 and 900,000 people at its height in the 13th century, which at that date makes it plausibly the largest urban complex on the planet, spread thin, green, low, not a walled city with fields outside it, but a continuous mesh of houses and ponds and rice land and infrastructure, with stone monuments standing in it like pieces of civic plant. Which brings me back to the towers. Angkor Wat itself, the one on the postcards and the flag, was built for Suryavarman II, begun in the first half of the 12th century and largely finished by around 1150. And do not misunderstand me, it is a staggering building. It is the largest religious monument in the world by area. The moat around it is roughly 190 meters wide and encloses a rectangle about 1.5 kilometers by 1 1/3. Estimates for the sandstone run to somewhere between 5 and 10 million blocks, quarried at Phnom Kulen, 35 or 40 kilometers away to the northeast. And here is the bit that made me sit up. How do you move 10 million blocks of sandstone 40 kilometers across a flat tropical plain in the 12th century? You do not drag them, you float them. The blocks came down by water on canals, and the survey work tracing those routes is pure logistics, which means the water network was not only the thing that kept the city alive, it was also the crane and the haul road, the infrastructure that fed the rice, delivered the stone, that built the temple that everybody photographs instead of the infrastructure. And notice which one came first. The channels and banks were being laid down for centuries before Suryavarman was born. Angkor Wat is a thing the machine made possible, sitting on the machine. That moat, incidentally, is not defensive and it is not scenery. It is a reservoir, and it is also groundwater management. A permanent body of water held against the foundations stabilizes the ground under an enormously heavy structure built on sand and clay. The most photographed reflecting pool on Earth is, functionally, part of the foundation design. So here is the inversion, and it has two halves, and the second half is the one that gets under my skin. First half, the temple is not the achievement. The landscape is the achievement. When you look at Angkor, you are looking at a piece of civil engineering with a cathedral standing on it, and we have got that backwards for a century because stone survives and earth does not, and because carvings photograph better than embankments. That is a correction, and the lasers have made it. But the second half is the interesting one. Ask what kind of machine this is. It is a gravity system, which means the whole thing is a program written in ground levels. The function of every single element depends on its elevation relative to every other element. This bank works because it is 30 centimeters higher than that channel. That reservoir feeds those fields because its water surface sits above them. The overflow protects the bank because it is set at that level and no other. It is a machine with no moving parts, no energy input and no controller, and that is exactly why it lasted 600 years, because there is nothing in it to break down. And it is also why it cannot be changed. You cannot replumb it. If the rain moves, if the river shifts, if the sediment builds, you cannot add a pump because there are no pumps. You cannot reroute the flow with a valve because there are no valves in the sense we mean. To change what this system does, you have to physically recut the ground over tens of kilometers and get the new levels right, across a plain that falls a meter a kilometer, with baskets in a hurry while the crop fails. And it is worse than that because the network is not one designer's work. It is 6 centuries of accretion. Every king added to what he inherited, and the additions assumed the existing levels, and the whole thing grew into a single interdependent object where nobody alive holds the complete drawing. In my trade, we call that a legacy system, and it is the most dangerous kind of asset there is. Enormously capable, deeply reliable, completely understood by nobody, and impossible to modify at speed. The capability and the rigidity are not two features. They are the same feature seen from different sides. This is the thing that made Angkor the biggest city on Earth, and it is the thing that made Angkor brittle. So what happened? Take the engineering evidence first, and I will be careful to separate what is measured from what is argued. Measurement 1. Sediment. A gravity network moving water slowly across a flat plain is a sediment trap by design. Slow water drops what it carries, and over centuries, as more forest upstream in the Kulin Hills was cleared and worked, more soil came down into the channels, and that process is written in the ground. Cores show silting, and one major canal in the south of Angkor that post-dates the 14th century is filled top to bottom with cross-bedded sand, which is not gentle accumulation. That is bulk sediment moving fast, the signature of a channel carrying far more energy than it was designed for. Measurement 2, and this one is dramatic. The Siem Reap River today is cut 5 to 8 meters down into the Angkorian floodplain. Down, below the level of the fields it used to feed. If your source river incises itself several meters below your distribution network, then your gravity system, the entire point of which is that the water starts high, has just been quietly disconnected from its supply. Not blocked, not broken. Disconnected by elevation, which for a gravity machine is exactly the same as switched off. Measurement 3. The climate. In 2010, Brendan Buckley and colleagues published a paper in the Proceedings of the National Academy of Sciences with a title that does not overclaim, Climate as a Contributing Factor in the Demise of Angkor. They built a hydroclimate reconstruction going back 7.5 centuries out of tree rings from southern Vietnam, and what it shows is not a gentle drift. It shows a mega drought running for decades from the 1330s into the 1360s, then a shorter but more severe one from around 1400 into the 1420s, and both of those punctuated by unusually intense monsoon years. Drought, then deluge, then drought again. Now put that on the machine. Drought first. Your reservoirs do not fill, and a raised reservoir that does not fill cannot feed anything, because the head is the whole mechanism. Meanwhile, the earth banks dry out and crack, and vegetation and maintenance both slip, because a system that is not delivering water is a system people stop turning out to dig. Then the deluge lands on a network that is silted, cracked, and undermaintained, and it does not politely refill it. It overtops it. It scours. It breaches. And in 2018, Dan Penny and colleagues published a study in Science Advances that did something I really admire. They turned the archaeological map into a network model and ran damage through it. Not a story, a topology. And the result is the one every engineer who has looked at an interconnected system dreads. Damage does not stay local. Break a link upstream and everything downstream loses function too, damaged or not, because it was only ever fed through that link. The failure cascades, and so does the repair problem, because the pieces you most need to rebuild first are the big earthworks that take the most labor. At exactly the moment the harvest has failed, and you have the least labor to spend. That is the engineering side reading of Angkor, and I find it painfully convincing. Not a city destroyed, but a city whose life support system went out of adjustment faster than it could be recut. And now I have to be straight with you, because I would rather be useful than dramatic. And this is the part most videos about Angkor skip. Everything I have just told you is one interpretation, and it is genuinely contested by serious people. Let me lay the disagreements out honestly. Start with the very idea of the hydraulic city. That phrase comes from the French scholar Bernard-Philippe Grosselier, who set it out fully in 1979, and it has been fought over ever since. From the 1980s onward, critics, Van Leer and later Robert Acker among them, argued that the Barays were nowhere near the grand irrigation engines Grosselier described, that there is no inscription anywhere that actually says a Baray was built to water rice, and that a lot of what looks like irrigation to a modern eye was religious and royal in purpose. A mountain and an ocean rendered in earth and water. That argument is not settled, and I will not pretend it is. My honest position, as an engineer rather than an epigrapher, a structure can be sacred and functional at once, and I have never met a society that moved that much soil for a metaphor alone, but I hold that loosely. Second, and bigger, the word collapse. In 2019, Dan Penny and colleagues published in the Proceedings of the National Academy of Sciences the results of coring the moat of Angkor Thom, the last and largest of the walled citadels. If a great city dies suddenly in the 15th century, that sediment should show it. It does not. It shows the signs of intensive land use, forest clearance, erosion, burning, declining from the early 14th century onward, a gradual withdrawal rather than a catastrophe. And by the end of the 14th century, the moat had gone over to floating swamp vegetation, which is what a body of water does when nobody maintains it anymore. So the administrative heart of the city was already emptying out before the events usually blamed for killing it. Related work by Alison Carter, Miriam Stark and colleagues shows Angkor Wat itself was never abandoned in any simple sense. People went on living around it and using it. Third, the sack. In 1431, by the conventional date, an Ayutthaya army out of what is now Thailand took Angkor, and the Khmer court subsequently shifted south toward the Mekong and the area around present-day Phnom Penh. That happened, but if the coring is right, that is a late event in a long story, not the cause of it, and the older telling in which foreign armies simply ended Angkor does not survive contact with the sediment. Fourth, there are rival explanations with nothing to do with water at all, and they are good ones. Maritime trade with China was booming, and a capital on the Mekong, closer to the sea lanes, is worth far more in that world than an inland agricultural one. So moving south may have been an opportunity rather than a retreat. And there was a profound religious shift through the 14th century toward Theravada Buddhism, away from the god-king state temple model that justified enormous public works in the first place. And if your society stops believing the king should command 100,000 people to dig, the digging stops, whatever the weather does. So here is where I stand, and hear the hedge properly. The water machine is, to my eye, the strongest engineering side reading, and the network modeling and the sediment work back it up. It is not the only reading. Several very good scholars weight the others more heavily, and even the word collapse is disputed by people who study this for a living and would call it a transformation. Nobody vanished. There is no mystery here and nothing supernatural about it. There is a country still there, whose people are still there, and a capital that moved. I tried the legacy system argument on Mike, my foreman, in the van, which is where all of my worst ideas get audited. I said the problem was that they could not replumb it. Mike thought about it for a mile and said, "So it is the old estate then." And he is right, and I had not seen it. There is an estate we worked on years back with a drainage layout put in by somebody long retired. No record drawings worth the name, and everybody knew that if you touched one gully at the top end you got water in a basement 4 streets away, so for 30 years nobody touched anything. Same disease, enormous accumulated capability that nobody can safely modify. Priya, our intern, asked the sharper question, as she does. She wanted to know why they did not build it more flexibly in the first place. And the answer should worry all of us, because for 600 years it worked. Every generation had direct evidence that the design was excellent because it kept on being excellent. Nobody re-engineers a system with a 6th century service record on the theory that the climate might do something it has not done in living memory. Flexibility is expensive, and it looks like waste right up until the day it is the only thing that would have saved you. And then I thought about the over-budget job, the one I do not enjoy discussing, the one that ran 200% over, because the single most expensive category on that job was not design error. It was every change we had to make late to a thing built assuming conditions that then changed. Retrofitting is where money goes to die. The Khmer were attempting a retrofit of a machine the size of a county, in a famine with baskets. So let me turn this round and point it at you, because I did not stand you on a 5-mile earth bank for a history lesson. You have built something. Not out of soil, but you have built something, and I would bet it works. A routine, a business, a career, a household budget, a way of getting through the week that has been quietly assembled and added to for years, and every year it works is a year of evidence that it is a good design. That is precisely the position Angkor was in. So the question is not whether it works. The question is the one nobody enjoys. What conditions is it assuming? Every system that runs without effort is running on assumptions, and the ones true for a long time go invisible, and invisible assumptions are the ones that take you down. So try this. Name the single condition your life is quietly built on. The income, the health, the person, the city, the arrangement everything else has been leveled against. And then ask the engineer's question, which is not could this change, because everything changes. It is. How fast could I replumb if it did? What would I have to recut? How long would it take me? And would I be starting with resources or starting in the middle of the failure with nothing? Because that is the real lesson of the Barays, and it is not a gloomy one. The Khmer were not fools, and they were not unlucky. They were superb. They built the most capable machine of their age, and its capability came from being enormous and hard-wired and gravity-fed and permanent, and every one of those virtues turned into a liability at the exact moment conditions moved. The lesson is not build less. The lesson is that somewhere in what you have built, you should keep a way to change your mind. So tell me in the comments, and I do read them, all of them. 2 questions. First, before today, did you know that the temple was the small part? That the actual structure was a water system the size of a modern city, laid out on a plain that falls a meter in a kilometer, with no pumps in it anywhere? Or is that as quietly outrageous to you as it still is to me? And second, the real one. What is the condition your own life is leveled against, and how long would it honestly take you to replumb? Say it out loud in the comments. Naming it is most of the work. I am off back to my own site, where I will be told that the attenuation tank has been value engineered and that this is fine. And I will think, as I now always do, about 700,000 people living on the output of a machine made of earth. No aliens, lads. No lost technology. No vanished civilization. Just extraordinary engineers who solved their century so well that they could not solve the next one. If that changed how you look at those 5 towers, or at anything you have built that only works in one weather, then subscribe and come back, because I have got another one still standing and still quietly making the rest of us look slow. My name is Dan. Mind the load. And the next time you find yourself walking along a low, straight ridge in the middle of nowhere, with a footpath worn along the top of it and nothing but dry grass on either side, do not assume it is a hill. Ask what it was holding back. Ask which way the water was meant to go. That is where the city is.